Good day, and welcome to P3, the GMAW Process Component and Execution. This program is meant for automotive reprocess people or people that are doing repairs on welds, and basically just people that are starting out and who need to understand the very basics of the GMAW process. So over the next little while, we're going to take this GMAW, gas metal arc welding apparatus, and we're going to break it into different components. We're going to talk about, of course, we're going to talk about the gun. The gun itself, that's the business end. That's the set, and you're going to hold and you're going to actually use your welding techniques to give us what we need. We always have to look at this power source. The power source is representative of the power to actually get us to do the welding. There's a number of different brands out there. We've all heard brands like Miller, Lincoln, Feronius, different companies that do the same thing, but in much different ways. We always have to consider, for part of our understanding of the process, the shielding gases. The shielding gases you're using are various. There are hundreds of different types of shielding gases that represent different ways that the weld actually becomes executed. We'll talk about those things a little more in some detail. The last part we're going to talk about is, of course, this wire and the wire handling system, which includes a way of pushing the wire through, and the wire acts as an electrode, and that's actually the proper classification for what the wire is, and this is what our weld deposit becomes. And of course, there's many different varieties of wire, and we know these as classifications. So the basic arc welding power source is a simple device, but it begins, and it always begins, as something we refer to as a type of a transformer. In this case, step down. You can't walk up to a panel and take electricity out of a panel and weld with it. It has to be converted into a different kind of energy. Now, this energy often shows up coming to the machine as voltage or current. Voltage and current should be seen completely separately. And depending on what process you're using, we'll be talking about what current and voltage do for us in the welding process. Now, when we take electricity from the panel and we push it into a welding machine, we activate something inside called the primary coil. Now, there's different versions and different ways to do this for most machines, but this is the basics of it all. So we take it out of the machine, we take it to the machine with high voltage and low current. Then these electrons come out and they spin around inside of a coil and they create magnetic inductance. And this magnetism affects another coil. And when we get to the other coil, we have converted high voltage to high current, and we've converted low current to high voltage, or to low voltage. So we've actually flipped them over. And what this does is, this gives us the current we need to make the welding process happen, because we need heat, and that will get us there. Now, this is how we make a deliberate short circuit. Now, the deliberate short circuit is the welding process. The only part of the entire welding process that should be getting hot is the plasma you create when you energize these shielding gases. So we'll get that to a little bit more detail later on. So your typical welding machine for the gas metal process is what we know as a constant voltage power source. So it's CV. Constant voltage power sources are almost used exclusively for wire feed processes. Now, each one of these machines, and whatever process you decide to study, if not all of them, there's a polarity. There's a DC. So we know this is a DC. We know this is a DC process, direct current. So it flows in one direction. It doesn't flip back and forth. Now, our DC CV process requires a number of different cables, especially with this process that's going to take us all the way from down at this lead. It's going to take us up to the box that controls our whether our gas is flowing. It controls whether our wire is running. It controls whether the output machine, this constant voltage machine, is giving us power or not, all simply by pulling that trigger right there. Right? So all these things happen automatically when you pull the trigger. So let's have a look at the actual contact tip diffuser. This is the business end of the gun. Now this is the end where we have these components we know as consumables. The contact tip itself is basically usually a type of a copper. There's different classifications of coppers used by different companies that do different things. And the contact tip itself turns into, or is held by, something we know as a diffuser or a gas diffuser. Now these two things work together. The contact tip electrifying the wire, because this is the point of contact where the wire becomes electrified. It's way down here at the end, just before it leaves, before this electrode, and there's the electrode right there, makes it into the contact tip. The diffuser distributes shielding gas and holds the contact tip steady and straight and uniform. This is especially important when it comes to robotic welding, because the contact tip, if it wanders, it will change everything to do with the location. Now, the real important part about this happens right in this area right here. So this is where we have something called extension. When we're tuning up a welding process, it's nothing short of tuning up a car. There's different conditions that you have to set it for. And one of the first things you have to understand is electrode extension. Electrode extension represents how far the wire comes out of this area here before it gets pinched off. And that's what voltage does. Voltage comes in and tries to pinch things off. And if it pinches it off right here, this all becomes plasma. This is the end where the heat is happening. Now the plasma end of itself is about 11,000 degrees. It's a theoretical calculation based on the amount of current and the ionized gas. Plasma has its own special place in almost every process, excluding resistance and a few others. But if there's an arc, there's plasma at play. And plasma is what's getting us our penetrations. The basics of shielding gases. Without shielding gases, we have nothing. Our atmosphere is not very conducive of any form of welding. There's 78% nitrogen, 21% oxygen, and almost 1% argon, which happens to be the gas that we use in welding anyway, but there's only 1% of it. So actual air is toxic to the welding process, so we have to replace it with something else. Now, when we take air and we break it into different parts, we already know what our concentration is. I said that about the 78, 21, and 1. So when it gets broken into these components, we actually take it through a liquid air process. A liquid air happens to be the process where they take air, and many companies do this, and they take air separation units and break nitrogen, argon, and oxygen into different parts. Now, they actually compress the gas, the air, into a liquefied form, and then, to simplify, basically boil it off, and they have different boiling points. All three of these have different boiling points. As they start to boil, they will deplete themselves from each level. You can see that nitrogen, liquid nitrogen, is minus 321 degrees Fahrenheit. That's very, very cold. We use liquid nitrogen for many things that have to do with making it cold. Argon itself, that's our base welding gas. It happens to be one of the 6 inert gases that were known. Argon, neon, xenon, radon, krypton, and helium are inert gases on the periodic table. This gas happens to be one that's in such abundance that we just use it a lot for the welding process. Oxygen's kind of the goal for all of these air separation units. Oxygen's required for medical. Oxygen's required for manufacture of steel. There's all kinds of things that go along with oxygen, including cutting. Now here's a typical cylinder, upright cylinder, that came from a project I was working on in Kentucky. And I was called because this particular cylinder has got two towers beside of it. So this has liquid argon in it. Now the liquid argon is extremely cold. And these two towers that are beside it are supposed to do the job of taking the liquid and give it an opportunity to boil back to temperature lower, or should I say raise, right? Raise, to get up to where it's boiling, and then turn back into a gas before it enters the plant. The concern here was that these towers had frozen solid. What had happened during this process was they were drawing the gas so fast because of a break in the line that it didn't have a chance, and it actually froze the towers solid. It was a very serious issue. So your shielding gas system is pretty clear. Your shielding gas has a source, whether it's a bulk system, whether it's a small mini bulk system where they deliver a liquid, or whether you're just on cylinders or bulk packs. It doesn't make much difference. You need a shielding gas system and a way of deploying it. The shielding gas system has on it a flow meter of some kind. Note I said flow meter, not a regulator. This process, the GMAW process, requires a flow, not a pressure. The flow is usually rated in cubic feet per hour, not per minute, per hour, or cubic liters per minute. Now, cubic feet per hour is very much the standard. Now, make no mistake about these flows that I'm throwing at you. You really need to understand exactly what you're welding before you can make an assessment of how much gas flow you need. Now, the gas flow does affect the weld, but you can overgas. Turning up the gas does not make a better weld. It doesn't change much of anything to the point where you can turn it up so high, it can become a contaminant. It can start drawing in atmosphere as a result of the turbulence. So the gas flow comes along and goes into a control. Now, we already talked about this trigger doing a bunch of different things for us. And that trigger, when you pull it, one of the things it does is it opens a solenoid in here that allows gas to flow down this hose and, of course, over and up into our gun and out into our area in front of the weld. So it keeps it surrounded or in this shield. As I say, once again, more is not better when it comes to this. Proper shielding and proper, like a breath, is all you need coming out of it. There are ways to assess this. Let me know if you wanted to talk about how to assess this. You can actually assess these situations on the fly. That is, you can put on equipment to tell you what the gas rate is, the flow rate is, or you could actually do it through the end of the gun and assess it before you start. Later on, we're going to talk about the 7 purposes for shielding gas, and one of them might surprise you. And here it is. The 7 purposes of shielding gas. We need to look at them because this gets addressed sometimes in the operational characteristics of the equipment. So we'll kick this right off with the first one I want to probably spend the most time on, temperature control. Your nozzle, your diffuser, your contact tip, all of these things are made from copper-based materials, meaning the copper is very conductive, and it tries to get rid of heat. It tries to move heat. If things get hot, it tries to move the heat and push the heat away as quickly as it can. Now, these thermally conductive materials will pick up heat, and it moves very quickly inside of this type of metal. The temperature control that shielding gas gives us is in the diffuser, you'll see a set of holes. Now, if you have a diffuser in front of you, or if you could get a diffuser in front of you, you'll see this set of holes and they go all the way around. We're going to have a better look at this later on in the presentation. But you see holes, at least 6 of them, going all the way around that basically blow the gas sideways against the walls of the nozzle, and hence trying to keep it somewhat cool. If I get an overheating contact tip or an overheating nozzle for whatever reason, I'll slightly boost up the gas. What I think would get to the point of excessive is anything over 40 cubic feet an hour. And by the way, if you're at 40 cubic feet an hour, I would expect you to be welding over 400 amp, and very few people from an automotive perspective are that high. Next, displacement of air. I've already mentioned that the air is no good for welding. The nitrogen in it, and actually nitrogen does have a reactive phase with hot steels. It actually likes to create very hard and embrittled surfaces. We actually nitride things. We do things to try to make surfaces a little bit tougher. So nitrogen isn't going to do us any good. We're still looking for that inert gas, a gas that does not combine with anything else. And that's what that list of noble gases does. It's a list of gases. That's argon, neon, xenon, radon, krypton, and helium. Those gases will not combine with anything else. They won't harm our puddle. They won't change our puddle. They'll change the type of plasma, but they won't change or affect the metallurgy. Probably only heat input would be changed, but any of them would be suitable for welding if you could get enough of it. We need to protect our base metal. When I was, I taught the colleges for 20 years, and I taught the apprenticeship programs. And what I used to like to do is, when a person was welding and training, I used to like to just shut the power off, just like that, quick, when they didn't know I was going to do it. And I did this so I could evaluate, so I could see a snapshot of what the person was looking at. Because one of the things I'm always looking for is a little tiny bit of undercut, a little bit of a crater out in front of your puddle. This tells me a lot about how you weld, actually. Do you keep the wire out where you should, out in front? Because your plasma needs to be making contact with base metal, not with weld metal. Because if it's making contact with base metal, you know you're actually making penetration. If you're just riding the wave on top of the puddle, and that's the biggest problem with MIG welding, if you go too slow, you'll create a lack of fusion. There's an over 70% failure rate in the GMAW flat position CSA test. And people are doing this, and people are having more and more issues just because of their stops and starts and their lack of fusion. It's very common that people try to weld way too slow. Remember, multiple passes, no weaves, no whips, and just get going. Protection of weld deposit. Of course we're protecting our weld deposit. We got to make sure it stays in that nice inert or semi-inert atmosphere. The weld metal that's behind the puddle is liquefied and it's cooling. As it's starting to cool, we have more and more issues because we have to make sure that that gas, that shielding gas, is actually there. If the shielding gas is somehow disrupted or something goes wrong with it, it turns into a big problem because we start getting contamination. That's why we'll be very critical during practical phases if you push or pull the gun too far. We'll talk about push and pull as a technique later on. But this area behind is an area we have to protect. Hence, we do not push or pull greater than maybe 10 degrees. When we add carbon dioxide, and we commonly add carbon dioxide to argon, we do steel welding. And when we're doing steel welding, we get a reactivity with the carbon dioxide. It actually helps to give us certain penetration profiles and everything that we want, and it has some metallurgical benefits as well. You will rarely ever see pure argon. In fact, I haven't seen Anybody using pure argon for MIG welding? If you ever thought you wanted to use one gas and it was inexpensive and something you were doing at home, carbon dioxide would be a good choice. Very good choice. And lastly, we need to create arc plasma. We need to create heat, right? And this is where we get into different types of gases that give us different types of heat. So it's something we have to consider. Okay, let's talk about some essentials of consumable electrodes. So you'll hear me talking, you'll hear many people just talking about it as wire, but always remember this, that these wires are electrodes because the electricity has to pass through them in order for us to get what we want. And that is, we need to electrify that space, that contact tip to work distance, plus the extension where the wire's sticking out, and we need it to actually grab electrons and start to develop that plasma to get the heat we need for welding. So this is your typical solid wire. Most people are using solid wire in automotive. There was a time not too many years ago for galvanized, we used metal cores and flux cores. Now, solid wires get the job done. Solid wires are just solid steel of a very specific metallurgical recipe, if you will, and a copper coating all the way around the outside. Now this copper is just pressed on and it can get scraped off. This is something I talk about with maintenance personnel when you talk about how to handle the wire, because you have to handle the wire very carefully. Now, the diameter of the wire always comes into play, and I always like to talk about it right here. Because a lot of people believe that if you have bigger wire, you can fill gaps. And it seems to make sense on the surface, but it defies, that philosophy defies physics. You see, when you have larger wire, as this diameter starts to grow, it actually supports more and more current, so it becomes more difficult to get it to start to create plasma. So we have to push, and it pushes our current higher and higher. When we want to weld thicker steels, we use bigger hard wires or bigger electrodes. So the bigger the electrode, the more current it carries. This is bad if you're thinking, oh, I'm just going to use a larger diameter to fill a gap. It doesn't work that way at all. So as we were just talking about, there's we have this these different wires. So there's ER70S6, ER70S3. Now, from the perspective of this program, I want you to know this. At this level of knowledge, I want you to understand that these are specific. That when that machine is running ER70S-6, that's what has to go back on it. Now, your engineering group, your quality group, and all of us have been very careful to make sure that we get the correct alloys, the correct classifications of materials, and when they're tested, because we actually have to make these parts, cut them up, test them, and we want to make sure these materials are correct. It could be a colossal mistake to put the wrong type of wire on this part or weld it with this part. So when a spool wire runs out or a drum of wire runs out, it would be everyone's responsibility to make sure that it was the right type of wire that went back on. Never make an assumption, especially in a plant that has some mixed wires. So just a quick pictorial to understand that the metal cores and flux cores had more penetration. Because this area, and actually the answer would be because these areas only on the outside, this is a tube, and the areas on the outside were the only areas that actually got electrified. So the arc density, the amount of power, is all on the outside, right where you want it, and confined to that area, so you always get more penetration on your outside edges. With the solid wire, you get a decent penetration profile, usually everything we need for the automotive applications that we're playing around with. Now, one of the things about and this is almost specific to the automotive industry. We have these welds, they go into place, and sometimes they get little bits. You'll look really close, and you'll see like little bits of glass on them. Now the glass is something called silicate. And silicate is almost imperative to every single time we weld something by liquefying steel. Silicate goes as far as being a deoxidizer for us. It has a number of different things that it does to contribute to a quality welding recipe, if you will. Right? So we're developing these different classifications, and silicate comes in different levels. Silicate happens to be one of those things that shows up in our concentration. If you go to CSA W48, it's a standard by which all wires, Canadian certified wires under CSA, they have their metallurgical consistency. They go through this, and silicate is one of the ones that change quite often. Now, in this particular case, I like to point out that it's there because it shows up, these silicate islands show up after the welding's happened. So after the welding's happened, and during the welding process is probably the best place to start, the silicate starts to mop up all the impurities that are around and try to float them out. So it ends up as like a very deep porosity inside the glass and not inside the weld. So the higher the silicate content in your wire or in your electrode, the more of these islands you will see. Now this isn't, with reprocess, this is not something you need to concern yourself with. This is not a quality defect or anything like that. It's just I wanted to point out to you because making sure we get the right wires is important. Some wires have a silicate content that's very low, and you would have very small versions of this silicate. Now, on the other hand, if we're going to talk for a moment about what the important one is, let's talk about the one that we'd never want, because hydrogen is our welder's worst enemy. If you have ever worked in the construction industry or anything to do with welding like that, you'll know that your electrodes, especially one known as 7018, is a low hydrogen class of electrode. And you'll also know that that electrode has to go into an oven. If that electrode is not put into an oven, we're pretty much throwing it out. Hydrogen, and that is hydrogen in the form of moisture, H2O, hydrogen and oxygen. Hydrogen, when it forms and it gets around the welding area, it actually starts to get absorbed into the puddle, and it'll create fine microstructure cracks, and it buries itself inside the material while it's cooling, and then it creates fine microstructure cracks while it's starting to come out. Now this, like many things in this presentation, probably require a bit more of an explanation, but that's as deep as I'm going to go on this particular occasion. Consumable electrode handling. So this is our consumable electrode handling. We, of course, have our source. We have a source of wire, which could come in a drum, a reel, spools. There's all kinds of different ways. We also have a conduit that keeps the wire intact. Now, this could be very, very short. You could have one of these spools that's actually mounted right on a machine. And then we have a set of drive rolls. There is a safety concern with drive rolls because I don't like anybody putting their fingers near the drive rolls at all unless I should say, the power is turned off. Now, why I say that is these drive rolls are very powerful, and they will take your finger right off. There's a gear ratio, and these are only 24-volt motors. They're quite small. But the ratio is very, very high, meaning that they develop, even though they're small, a great deal of power. Sometimes you got to pull this spool here, and it weighs 44 pounds, and there's a bit of a friction break. We got to have some power here, right? So what you got to make sure you do is you make sure you turn the power off and don't go anywhere near these feeder rolls until you know that the power's off. Probably not a lockout tagout. Probably enough to make sure, just to make sure that the power is turned off during the any type of maintenance you would do there. I was witness to an accident. I'm actually a licensed paramedic as well, and I was witness to not witness, but I was at an accident where a person had been changing a spool of wire, and somebody who was in a hurry was pulling the trigger, playing with the trigger, and the person caught their finger and actually took their index finger off. So there's some pretty serious stuff that goes along with this, right? You can really get hurt. Power off before you touch anything. So one of the things we're dealing with here are these drive rolls. There's different types of drive rolls for different types of equipment. The normal equipment you'll see for steel type drive rolls is a V groove. If you were going to go to a more high-end machine, for example, a Fronius, you might have a U groove drive roll that wants to put even pressure on the electrode and try to reduce the forces you would get from just having 2 points of contact from your standard. That being said, the Fronius equipment usually outperforms all those other equipments as a result of a number of different things, which most agree has to do with keeping the wire as intact as possible. And this certainly would keep our wire intact as possible. Remember, I said the outside coating on this wire, it will flake off if it gets any friction or anything goes wrong with it. So we have our V groove and U groove. We always got to make sure we keep these clean. Most companies, whether this one happens to say it's aluminum, because we do this with aluminum as well, but it's the same problem no matter what. Our drive rolls have to stay clean. If your drive rolls get dirty, they start to push dirt and grime and anything else that might be around, they start to push it back into the wire. When they push it back into the wire, they're actually creating a rough surface. And that rough surface has to eventually go through the contact tip and become electrified. And when it becomes electrified, then we get our weld. But if that surface is terrible, if it's been chewed up by our drive rolls, whether our drive rolls are dirty or they're just damaged drive rolls, it has to be addressed, because it will bring you to a stop and you'll be struggling all night trying to figure out why this machine won't work. I've put in there, there's a something called a V-groove knurled drive roll. And the knurled drive rolls are basically for much softer wire. You should not see these ever on solid wire. Please let me say that again. You never see V-groove knurled drive rolls or any type of bumps in a drive roll if it's a solid wire. Okay. Wire deposition. This is the deposit of your electrode. This is your electrode leaving that extension. When it gets melted off the extension, remember the extension is how far it comes out of the gun. And then it gets pinched off by the voltage and it has to take this trip. And these are the types of transfers. Now, almost everybody is going to be welding in short circuit if you're doing reprocess on automotive components that are only a couple of millimeters thick. You're welding in short circuit. That is, your voltage is so low that you don't keep blowing holes right through it. Now, the short circuit process is basically referred to as because the wire actually makes contact with the surface and creates a short circuit. This is for cooler parameters where we're trying to, deal with some bad welds, some burn through, allowable, of course, burn through that the specification says you're allowed to fix. I want to make a distinction there. So this is for the lower end and the thinner types of materials. The next step is globular transfer. The red line right here represents our voltage. So our voltage is down. Now our voltage is starting to go a little bit higher. Now the wire feed speed is changing a little bit too. But the globular transfer is kind of special, so I want to take a moment on it. Globular transfer represents a danger to welding because you can actually turn the wire feed speed down a little bit and get a weld that looks much better. It doesn't have as much spatter, but it has absolutely zero penetration. I listen for a sputtering sound in every welding process I'm listening to for GMAW. There's a very distinctive and uncharacteristic sputtering sound that happens when there's a deposit of these large globules going to a base metal. Now, the globular transfer has its place, but it's not for welding steel to steel. It can be used with welding bronze commonly, where we don't want penetration or want very limited penetration. But globular transfer is not what we're looking for. Now the last one is known as spray transfer, where the globulars become very, very small and they're pinched off the wire and they're coming very rapidly. Now, we've hit a point now where the wire feed speed is up and the voltage is up, and now the wire can't make it. The voltage is too high. The wire can't make it to the base metal before it gets pinched off. So now there's good plasma concentration. The wire's not out in front of us. We're not making spatter by bouncing the wire off the surface like we did in short circuit. So spray transfer is exactly where we need to be. So here's all these processes, except for I've added one. I would say, and this is my opinion, that robots would never be what they are today if it weren't for understanding how to use pulse. Pulse is like a heartbeat. That's what this is here. It's like a little bit of a heartbeat that helps us to define where the wire gets pinched off. You can control this. You might have even been welding gas metal and heard a robot running and heard it like a tone, like there's a little bit of a tone, and some of the tones even sound different. Pulse spray is that tone. That tone you hear is the frequency of these pulses that run behind it. What this does is it gives us complete control over the pinching of the wire. As I said, the voltage comes up and pinches the wire off as it's coming out. This gives us complete control over how that pinch works to make sure that it's a clean dispersion and the droplet itself goes right to the place where it's supposed to be. And what this does is this controls spatter especially. It controls heat input. It controls whether you're penetrating or not penetrating. The pulses are all written based on a specific diameter and classification of material. So that's why if you went online, you could go online with Fronius, for example, and you can find programs that are online you could upload to your equipment. I think the same thing could be said for almost anybody now. I know Lincoln and Miller allow that to be happening. So you can actually go online, take a memory stick, get a different pulse program, take it back, and run it. Some materials are very finicky. I'll give you an example of one, stainless steels. 300 series stainless steels are very finicky. They want very specific programs. Best I've seen in this particular category, Fronius. Secondary grounding. Now we have to consider secondary grounding is where we put our ground clamp. So let's talk a little bit about resistance here and why it's important that we have a good connection. This is a gas metal arc welder. You can see drive rolls flying around, spinning very, very quickly. The wire was passing through this area here, in this particular case, at 550 inches per minute. So it's really coming out of there. Now, I got a phone call because there was something wrong with this equipment. It wasn't running properly. And we were to discover that there was a short. There was a bad connection somewhere inside the feeder. You can even see right here, you can even see that it was starting to melt all this aluminum casting. What's bright there in the center, that's a bolt head. The bolt head was getting so hot because there was something else that was resistant inside the process. So they were having problems at the other end with the welding, but what had happened was they were losing current. This causes a bunch of different problems when you have a bad connection. The bad connection you want is right at the wire. That is the worst possible place that you could have to get your plasma and keep your plasma as concentrated as possible. Any other area inside your welding area, inside your welded circuit that gets hot, causes more issues. Now, the more you weld in a certain place, the more magnetism you make. Now, this is just a set of cutting pliers, and I thought, oh, these have been sitting here for a while. Clearly, they've picked up a whole bunch of magnetism. These didn't come to us magnetized. They become magnetized when they get exposed to DC, direct current welding current. It doesn't matter if it's DC for stick welding with what we call constant current or whatever. It's DC. It gives us and helps to build magnetic phase. And that is, how much magnetism does it start to collect? Now, with steels, certain metals, will collect this magnetism and hold it for a long period of time. Certain materials will hold it temporarily. You can temporarily magnetize a screwdriver to hold a screw in place with a good rare earth magnet. So there's all kinds of things you could do with it. The problem is, when you get too much magnetism, it starts to cause problems to the automotive industry. Because the automotive industry has a problem with a condition called arc blow, and it's very seldom seen or described. But here's the call that I get about their welding cell. They call and they say, Bob, we've got a welding cell. We've only been running for a few months. Now we're getting into some big numbers. We're starting to run really hard. And after a couple of hours, for no reason whatsoever, the welds start going off location. Now, why am I telling reprocess people, reprocess specialists, you will be, why am I telling you this? Because you're the first person to see it. Your communication about welds and how far welds go off location is very important, because you might pick this up. So you look for trends. I consider anybody that does reprocess in an automotive environment to be one of a very important asset, as long as they pay attention to what's going on. And if I'm working as a robot tech, your input would be helpful, because they might go in. You might say, I've got these welds and they've gone off location. Somebody goes in, they look at it and they go, we're not off location by much, right? Or they might say, this wire is exactly where it's supposed to be. Often we blame a part shift or something like that, but pay attention to the timing. These things only happen when it runs hard. Sometimes they'll stop for 10 or 15 minutes, everybody will do something, and the magnetism goes away all on its own. That's what I always say if I'm doing my troubleshooting programs. I'll say, if you have one of these conditions and you think you're starting to build up magnetism because the magnetism is pushing the weld around, and it does, just shut the cell down for 10 minutes when this happens. Go clean up, do something else, and just turn it on and see if it goes back. If it just goes back, you're building up magnetism. It's as simple as that. And if you want to see what it looks like, if you went inside, this is what it would look like if a robot tech went in there quickly while the phase was still there, grabbed the helmet, and watched it weld, and you would actually see the plasma coming off the side of the wire. Now, we've seen this. I was a pipe welder for well over a decade. And we see this in pipe welding all the time, because sometimes we spend an enormous amount of time welding on one piece of pipe. And if you don't change your ground around, sometimes you're going to be in trouble. And there were often we had to run cycles of welding current in a different direction, or sometimes AC, to try to make it so we didn't have as much. Certain electrodes, like 7018, under special circumstances, they have it available to be run in AC, and sometimes you got to run one shift like that just to try to break up all of this phase. If you ever want to have some fun, and please do it gently, when a person's about to weld something, and it's not a test or anything like that, don't do this to a person on a test, but take a rare earth magnet and stick it on the back of their coupon before they start to weld. As they start to weld, you're going to see everything going just fantastic, and wait till you see what happens when it gets to that magnet. It's going to push that material all over the place. It's an interesting thing to see, if you can understand it. So, arc welding, ground clamps, what can I say? It's very important to grounding systems. It doesn't matter if it's something you're doing by hand, as in a semi-automatic process where you grab the gun and you pull the trigger, the wire comes out. That's why they refer to it as semi-automatic. Or whether we're looking at grounding a robotic system. Ground should be solid. Ground should never get hot. All of these things, any type of temperature buildup inside of your welding circuit is going to give you trouble. Now, take caution with welding grounds that are just stuck on the side of a bench. Make sure that they're connected very well. I think this is a good time to talk about a safety concern I have as well. When in the welding process, if you happen to get electrical shock or anything, when you're doing MIG welding, it's relatively safe. If something should happen and you start to get electrical shock, though, what happens is usually you clench. Usually your hands clench if you're under the conditions of an electrical shock. Now, when you clench your hands around that gun, if you were to get an electrical shock and you're clenching your hand around that gun, there's no way to help you because you've got your hand pulling that trigger. And the ground, and it might be burning up, and you might be kind of in the way of shutting it down. One of the things I like to do, especially if the welding machine is not really, really close, where the safest thing to do is shut it off. But if it's not really close, one of my safety features that I like is a ground I can see. Now, I get this habit from stick welding where that ground decides whether my machine is basically off or on, and sometimes I'm hundreds and hundreds of feet away and up in the air. But the ground itself, remember the safety feature of a ground is it clips on. It's got a good spring tension, but you could also remove it very quickly. And I think that's the best way to look at it. Contact tips and diffusers. There are lots of different contact tips and diffusers out there in configurations. Let me tell you a couple of points. First off, there are wires out there that you don't need this nozzle on the outside. You don't need these nozzles. These copper or bronze, it's copper. You don't need these pieces at all. You can actually just have wire coming out, and the wire itself is its own fluxing agent. We refer to these as flux cores. But metal cores and solid wires and some flux cores require some level of shielding gas, so we have the nozzle here for containment. Now notice some are in, some are out. Right? There's different configurations. This one happens to be flush. So this is our situation. We don't know what everybody is going to be doing. If I'm setting up a robot, I want to give the robotic operator the best opportunity to control his contact to work distance. So often I will have the contact tip sticking out, contact tip sticking out, contact tip sticking out. I'll have these contact tips sticking out a little bit to give that robot programmer some clearance so they can get into different places you might not be able to do, because the important part, make no mistake, I'm back to contact tip to work distance. That's why your understanding and your skill set in operating this equipment controls the penetration. I could sit here and talk all day. If you don't have good contact tip to work distance in your process, there's a problem. So there are also some funny ones with a little bit of a taper on it. We try to avoid these very much. All these ones with a taper, the tips of them like to melt very much quicker than the ones that are big and round and smooth. But this taper on the nozzle, on this particular one especially, this area in here gets too small, and the shielding gas coming out doesn't have velocity. We always have to remember that shielding gas, remember I limited you before and I said be careful how much gas you put on it. And that's true if you confine the area of the gas coming out too and create velocity. I don't want velocity, I want presence. You could weld these things without any nozzle at all. You could fill a chamber full of this gas, and just its presence and its method of dispersing all the other air around it to make sure it's only this particular mix is all you need. So there's different types of diffusers. Now, we talked about diffusers earlier in the presentation. I wanted to show you this part right here. All of these diffusers have a way of releasing the gas. In the gas metal process, almost always, there's a liner that comes down and brings the wire down to the front of the gun. Surrounded by this liner is a hose, and the hose carries the gas. That brings it so it comes out here and gets dispersed through these little holes in the diffuser. It blows the gas straight out, and of course, here's examples up here where it blows it out and blows it straight up against the walls of your nozzle. What they're trying to create from these situations is a barrier for heat. So the heat has to get past this area. And we're trying to control all the heat that's generating here and moving back this way and keeping it away from all of our seals and connections and everything that's back here. It's usually more than enough. There is a rubber seal. You can see them down here. There's a rubber seal that needs to be in your gun, that needs to be on your diffuser, because it will keep the gas from flowing backwards or starting to blow around these metal retainers here in the end. Here's a typical contact tip. The typical contact tip that has been overheated. I was saying before about the contact tips themselves. The contact tips themselves pick up enough spatter on their own without having an overheated condition. So these contact tips have a taper. This particular brand has a taper in it. Because it has a taper, we've lost mass. Mass has been taken away from this contact tip. The thicker the mass, the more difficult it is for this area to reach 1600 degrees Fahrenheit. That's the point where copper starts to melt. When this copper gets to a certain point, it actually starts to pick up spatter. When it gets to the point of almost melting, so when we start to liquefy it, it starts to actually stick to the liquefaction point. Now this is a chrome zirc tip. It's a special type of a hardened tip. And we know this because it has a band around it. All chrome zirc tips have a band around them. So this one was picking up so much heat and was getting so hot from the plasma, and failure came as a result of course, the spatter ball sticking to this cluster that's building on the side of it. This is an overheated condition that should be addressed through technique, parameters, whatever, or maybe clearly just a bigger, better contact tip. Now this is a picture I've taken of contact tips from behind. And one of the things I like to point out to everybody, especially when it comes to a robotic perspective, is controlling the wire and the control of the wire as it passes from your drum or your spool or your reel and makes its way to our contact tip. All of these wires have a special coating on the outside of them we call post-finish. Every company who complies with CSA W48 give us a piece of material that is correct in its metallurgical presentation, but all the companies have a different method of creating this post-finish condition on the outside of the wire. How thick is the copper? The type of copper it is, how fast it's put on, how much of this post-finish, whether it's a type of a wax or a type of an oil, whatever it happens to be, all these things have to be controlled. Now you, or all of us, when we load up all of our equipment with these wires, it comes at a price, because we got to make sure that we handle this in such a way that if we are scraping it in any way or shape or form between now and when it gets to the contact tip, this post-finish that's responsible for how these things run will start to create micro-arcing inside, right? So what happens is, this is the bore, this is the hole, the orifice where the electrode passes through. When it goes through, there's little explosions that happen because it doesn't have good conductivity on the outside. We've scraped off the post-finish, or our drive rolls have embossed that wire to the point where it just doesn't conduct as well as it should. Furthermore, it might just be purely dirty or roughed up. If it is, it's going to start to elongate the contact tip like here. So there's an elongation, right? This last one down here, I'll point out, this is what happens if you don't use any post finish. If you take all these all have and this is actually a specific brand that they don't use or didn't use any post finish at the time because they didn't feel that they needed it. And this is the type of micro arcing we would see. Now this is the inside of a diffuser. Now the diffuser has this unique string of holes that go around it that the gas disperses from. Now if you're setting up a robotic application here, one of the things we're doing is we're running spray programs, or that is programs where there's a reaming station that we present the front end of the gun to it. It grips the gun. It has a reamer that goes up. It's like a drill configuration. It goes up and cleans the nozzle to make sure the spatter's off of it. And then it goes over and it usually gets a spray. There's a special spray that you can put on the nozzle that that gives it a little bit of a residue that the nozzle itself doesn't like. It cools the nozzle off. It gives it an opportunity to form a bit of a barrier against all of this spatter that could build up on it. Now, if you spray too long or too hard, you'll actually push the spray right back up inside the nozzle. And if you push it up inside the nozzle, you'll push it up through those little holes in the side, and you'll push it back into that cavity in the diffuser. This is a picture of the diffuser looking down inside after a gun had been set up to go and get reamed and sprayed, and it was being sprayed way too hard. The spatter got through the holes and just kept filling up inside the diffuser to the point where it actually baked itself on. You could pick that off pretty good afterward, but clearly it was being sprayed too hard. Now all these bits of spatter will also accumulate inside the back of that contact tip that we looked at before. So this particular machine is going to be struggling constantly. So that's the end of this segment. You could always contact me regarding anything to do with this presentation. Always remember that there's an opportunity. If you want, I could send you other documentation to do with this program. You could have a copy of this program as a result of taking the program. I will send upon request a PDF form of the presentation. So if there's anything else I can do to assist you, please let me know. And thank you very much for your time.